Now let's consider conjugate bases and acids. So if I have an acid, HF, and it will react with water in an equilibrium to produce H3O plus and F minus. And this is what we call the conjugate base of our acid, HF. So the conjugate base acts like a base. It will be a proton acceptor. So if we could get F minus by itself in solution, it would behave like a base. So one way of doing that is to form the salt of the conjugate base. So sodium fluoride is a salt, and if we put it in water, sodium fluoride will dissolve in water to give sodium ions plus fluoride minus ions. Now the sodium is a spectator. There are just a few spectator ions that you just need to remember. Sodium is one, chlorine is another, the most common ones. But the fluorine minus is not a spectator ion, it is a base. And so if you have fluorine minus in solution, it can react with water, and since it's a base, it will accept a proton to produce HF and the resultant OH minus ion. So here we have a base reacting with water to produce its conjugate acid in solution. So now we have an equilibrium expression for this particular reaction, and we'll call it K sub B, since it's K for a base. And how is that related to K sub A? Well, we can determine that by considering two separate reactions. Now let's consider the reverse of the K sub A reaction with HF. So we have F minus plus H3O plus in equilibrium with HF and water. So we know the value of this equilibrium constant. It is 1 over K sub A. Since we've written the reaction reverse, we take the inverse of the equilibrium constant. Now consider this other reaction. We have water autoionization. And the value of it, this equilibrium constant is K sub W. Now let's add these two reactions together. So I'm going to have one of the waters cancel because they're on opposite sides of the arrows. The H3O plus will cancel because it's on opposite sides of the arrows. So my resultant reaction will be this. And so if I add reactions, I multiply equilibrium constants. So the equilibrium constant for this base reaction, K sub B, is going to be 1 over K sub A multiplied by K sub W, or just K sub W over K sub A. So now, knowing the K sub A for an acid, I can find the K sub B for its conjugate base just from this expression, knowing K sub W. So, in our case, K Ka for HF is equal to 3.5 times 10 to the minus 4th, and that means Kb for its conjugate base, F minus, is equal to Kw over Ka, which is 10 to the minus 14th divided by 3.5 times 10 to the minus 4th. So this is equal to 2.9 times 10 to the minus 11th. So this is much smaller than the K sub A. So this reaction proceeds to a much less extent for F minus than it does for HF. We can do the same thing for a weak base. Say we have the base ammonium ion. Ammonia. I need to start over. Ammonia NH3. It will react with water to produce the ammonium ion, OH minus. This has a particular Kb value. Now, this is a base. This is the conjugate acid. Now, what if we took ammonium chloride? This is the salt of the conjugate acid. We dissolved it in water. It will produce NH4 plus aqueous plus chlorine minus aqueous. Well, we already know that sodium plus and chlorine minus are spectator ions, so does not participate in any further chemistry, and therefore we have the NH4 plus ion, which is an acid, and so in water it will behave as an acid and donate a proton to water to produce H3O plus and its conjugate base, ammonia. Now we can do a similar adding of reactions, where we take this reaction and we add it to the autoionization of water, and we will get K sub A for the conjugate acid is equal to K sub W over K sub B. So this would be 10 to the minus 14th over 1.8 times 10 to the minus 5. That's the Kb for ammonia. So that gives 5.6 times 10 to the minus 10th as the Ka for the conjugate acid of ammonia, the NH4 plus ion. So we can see the relationship. The stronger the acid, the weaker its conjugate base. And the stronger the base, the weaker its conjugate acid will be.